issues, so I can't access YouTube. That's why I've not been able to download the recording. I mean, that's why I've not been able to upload the recordings for last weekend. But I'm working on it, and I promise anytime it is sorted, I'll be able to upload the videos and I give you the links to the videos. But the e-learning platform, I've been able to upload the lecture notes for this chapter 3 that we are discussing today. And I also uploaded the presentation. So when you go there, you just see the presentation. And in both courses, I put presentations for last weekend. Okay. So I hope you got a chance to go through these notes that we are going to discuss today. In chapter 3, we'll be talking about inner product spaces. We'll be talking about inner product spaces, and this is going to be our plan. We'll define inner product spaces and give examples. Define the length and distance in inner product spaces. We look at the properties of inner product spaces. We look at angles and orthogonality. We define what it means for two vectors in an inner product space to be orthogonal and orthonormal. We have orthogonality and orthonormality. And then lastly, we talk about the orthogonal complements. Now, when we talk about a space in mathematics, we are referring to a set with some operation defined on that set satisfying a list of axioms. When we talk of a space, we are referring to a non-empty set with an operation defined on the set satisfying a list of axioms. So we start with a vector V from the set of real numbers or a real vector space. So V is a vector space. Suppose to each pair of vectors, if you pick two elements in that set V, there is a function. If we can find a function that assigns a real number denoted by UV with that notation, then this function is called an inner product if it satisfies the following axioms. So the inner product is a function, just like we looked at a linear function last time. Last time we said a linear function has one of the properties that when you give it a vector, it computes and it returns a scalar. So likewise, the inner product is a function. When you give it two vectors uv, it returns a number. So if this function satisfies the following axioms, for every u vw vectors in V and for every scalar lambda, then 1. So we are going to list the axioms by I1. The capital I stands for the inner product space, and the I1, it is the first property. There are 4 properties, and because we will be referring to them throughout this work, that's why we are labeling them I1. I1. So I1 is that the inner product of U and V is the same as the inner product of V and U. And that property is called the symmetry property. It is the symmetry property. The second property, which we are calling I2, is the additivity property. It is the additivity property that the inner product of U plus V and W is equal to inner product of U and W plus the inner product of V and W. We call that the additivity. We have another property, I3, which we call the homogeneity, that when we take the inner product of U times a scalar lambda and V, then we can pull the scalar outside, then we take the inner product of U and V. We have I4. I4 on my slide is not clear, but we shall see it as we proceed. But what I4 says is that the inner product is non-negative. The inner product of U and V is non-negative. Actually, I4 relates inner product of the same vector. So the inner product of U is always non-negative, and if it is zero, then it means V is zero. The inner product can only be zero if we are looking at a zero vector. So if um, a function defined by inner product of U V, which maps elements in V and returns scalars, if it satisfies these axioms I1, I2, I3, and I4, then that function qualifies to be called an inner product. And vector space V with the inner product defined on it is called an inner product space. We have an example. If you have a query, as usual, please hit the raise up hand button. I'll be able to see your hand, or you can unmute your microphone and talk. So we have an example here. In this example, we are talking about two vectors U being U1, U2 up to UN, then V1 up to Vn. They are vectors in Rn. So our vector space is Rn, and we are defining a function, the inner product of two vectors from Rn. Of course, it picks two vectors, so it is Rn plus Rn, and then it returns R. This is supposed to be R. Sorry about this typo, because when we compute, we should return R. We should get R, not Rn again. So if that inner product is defined by this, then it defines an inner product on R called the Euclidean or the usual inner product. Now, when you look at this definition, this is the usual dot product, the dot product we learned in vectors, in vectors in linear algebra 1. So this is the usual dot product. It says if I take the dot, it's defined by dot U dot V. U dot V means I multiply component wise. It is U1 times V1 plus U2 times V2 plus U3 times V3 plus, and so on up to UN times Vn. So this is the usual dot product, and that inner product is called the Euclidean or the usual inner product. Now, to prove that the vector space, to prove that the vector space Rn with this inner product defined like this becomes an inner product space, we need to check the other four axioms, I1, I2, and I3. So in the proof, we check the axioms. So we are going to pick three vectors in Rn, that is U, V, and W, and then we pick a scalar lambda. So I1, it says that the inner product of U and V, we called it the homogeneous, the symmetry. The inner product of U and V, it is supposed to be the same as the inner product of V and U. So we compute the inner product of U and V. It is the same as the dot product of U and V, which is the sum from I is 1 up to N according to our definition, because when I come back to this definition, it says this dot product is given by this, but we see here we are summing from I is 1 up to N of Ui, Vi, because when I is 1, I have U1, V1 plus. When I is 2, I have U2, and so on. So using that definition, the inner product of U and V is going to be this sum. But I know when this multiplication here, since multiplication is commutative, multiplication is commutative, taking the product of ui times vi is the same as taking the product vi times ui. And when I reach here, I see that this is the inner product of v and u. So that means that the symmetry property holds. Next, I check I2, the second property, which is the additivity property. I take inner product of u plus v and w. And from the definition, this is the u plus v then dot w. And then again from the definition, this is the same as the sum, like this. And again, here we can open brackets. So we have uiwi plus viwi. So when we taking the sum is a linear operator, a sum is the same as taking the sum on each term. So we sum here and we sum here. So we can see that this defines that, and then this one here defines this. Thus, we get I2 also holding. Okay, next we check I3 and I4. I3, I3, we get the inner product of a constant lambda u then times v, and we know that that is the same as taking the product as shown here. And then from the definition of the inner product, we can take this sum. This is supposed to be I, sorry, it is, okay, yeah, this is I equal to 1 up to n, so we have this. So it is the same as this multiplication. So we can put the constant outside the sum here, and what we have, so really even I3 holds. Next is I4. I4 we take the inner product of v and v. This is v dot v, and this is the sum. Since we have v, so we have vi squared, and we see once we square anything, then it will always be non-negative. Because it is squared, it means it will always be greater or equal to 0. Because even if it was a negative, when we square it, the result is positive. When you square positive, the result is positive. And moreover, if the inner product here is equal to 0, if and only if v is 0, so that is I4. So since this inner product here, since this function here defines an inner product on Rn, so thus this function defines an inner product on Rn, and we called it the Euclidean or the usual inner product space. Example 2, we have a vector space V equals C AB, which is a space of all continuous real valued functions defined on an interval AB. So we are defining a function defined by the inner product of two vectors from V to R. So we pick vectors, then we return real. So this function is defined for two functions, f and g. It is the integral from a up to b of the product of the functions with respect to t. And t is a number between a and b. And so we are saying that this function defines an inner product on this vector space of all continuous functions defined on a given interval. So likewise, we start with the I1. Let H be three functions in our space. Remember, V is a space of all continuous functions. So it means FGH are continuous functions, and are continuous functions, and lambda is a scalar. Then we check the symmetry property 1. So the inner product of f and g from the definition, it is the integral from a up to b, then product here. But we know when we have a product of ft times gt, it is the same as gt times ft. And from the definition, this is the inner product of GF. So that means I1 has been checked. Next, we check I2. I2 is the additivity property. We add F plus G, then H. We find its inner product. By definition, this is the integral from A up to B of, like, we are put T, then HT, but this T can be distributed inside, so we have F of T plus GT outside HT. Again, we can take H inside, so we have this integral F of T times H of T dt plus GT HT, and this gives us that. So the additivity property also holds. Next, we check the other two properties, that is I3 and I4. So I3 is the inner product of one of the vectors times a constant, then times G, and that one is defined like that, and we get the constant out. So I3 also holds. Next, I4, it is the inner product of the same element, which is FF. So it is the integral F of T times F of T, which is F of squared dt. So since F squared, for anything we have here, once we square, we'll always get something which is greater than 0 for any value of T in that interval. Now, for I4, we are meaning to check that the only way this can be 0, we are meaning to check that the only way this can be 0 is when F is a 0 function. So suppose this inner is equal to 0, then it means this integral is equal to 0. And since already from part 1 of I4 we showed that this is non-negative and F is continuous and non-negative. So it means that to integrate this as 0, it means F of T is 0 for every T in T, meaning that the only way this can be 0 is if this is 0. So when we are checking I4, we check two things. We check that the inner product of FF is non-negative, i.e. greater or equal to 0. The second thing, we check that the only way that inner product can be 0 is if the element itself is equal to 0. So this is another example. This is another example. It's another example. We have V, which is Rn, and for any vector, for any two vectors U, V, in V we are defining the inner product of U and V as the V transpose times A transpose, then A times U. This first V is the V for the element. This should be the V here, not the capital V. Where A is an n by n matrix. Then we are defining an inner product on Rn. So this inner product, okay, this defines an inner product. Defines an inner product on Rn. This inner product is called the inner product generated by matrix A. So when we get V transpose times A transpose times A, then times U, we get an inner product which is known as the inner product generated by the function A. This is the third example of an inner product. The fourth one, yeah, it is known that every polynomial is continuous function. Polynomials are continuous functions. That is a known fact from calculus 1. Thus, if a polynomial Pn is the vector space of polynomials of degree less or equal to n, if Pn is our vector space of polynomials of degree less or equal to n, defined on a closed and bounded interval AB, then the inner product PQ, this is PQ, defined by the integral from A up to B, PT times QT dt, PQ in Pn, Pn is a vector space, and T in that closed and bounded interval. This one also defines an inner product space, defines an inner product on Pn. and then Pn with that inner product forms an inner product space. So this is the fourth example of the inner product space, and you can prove it. The proof for this can be, the proof for these two can be worked on, and it is easy. We follow the criteria we used in the previous two examples. We need to check the other four properties in the definition of an inner product, that is I1, I2, I3, and I4. Okay, any questions? Any questions, please? Are we still together?
Yes, sir, we are together.
I'm following.
Okay. Irene, how are you? Irene,
Yes, please.
how are you?
I'm fine, Master.
Last weekend I saw you kept trying to enter, but you did not succeed. What was the problem?
I think my network was poor that day. I really don't know what had happened.
I saw you. I kept seeing you trying to enter, and I would admit you, but nothing. But thank God you're now present.
Amen.
Okay, so the next thing we want to define the length in an inner product space. Of course, we know length as a scalar quantity, but we want to define it. We want to see a notation for the length in an inner product space. Um, um, from axiom 4, you see, length cannot be negative. So we are going to define length from axiom 4. Remember, axiom 4 says in an inner product space, okay, in a vector space V, then the inner product of V is always non-negative. So that means that this value that we get from this function, the square root is well defined, because when we take the square root of a positive thing, it is well defined. So it follows, it allows us to define length of a vector V in an inner product space V. So the length, if V is an inner product space, then the norm length is also known as the norm of the vector U in V is denoted. So once we find this, then we know it is standing for length or the norm, and it is denoted by this and is defined by the square root of the inner product of U. And the square root can also be written as this inner product to power a half. So we can use this or that. So this is what we call the length in an inner product space. It is called the norm. Next, we want to define the distance. The distance between two vectors U and V in an inner product space is given by this notation. It is DUV. The D is distance. So this is distance between U and V. And we know that this is the distance between U and V is the length or the norm of U minus V. This length, whether we start V minus U or U minus V, if it is a negative, then this norm will always be positive. So it's like if I want to know the distance between which distance is okay between Entebbe and Kampala, then I get the distance at Kampala. I subtract the one from Entebbe. Oh, Entebbe to Kampala. So assuming that I start, I think it's around 38 kilometers from city center to Entebbe. So if I start from Kampala, then I'm starting from 0. By the time I reach Entebbe, those are 38 kilometers. So I get 0 minus 38. When you do that, you get a negative. But because I'm taking the norm or the length, it will give me the positive. So either 38 minus 0 or 0 minus 38 gives me that distance. So from the definition of this norm, it is the inner product of u minus v, then u minus v again. And if u is a vector in an inner product space V such that the norm is 1, then u is called a unit vector. So here we are defining three things. One, we've defined the norm or length of a vector u in an inner product space V. Two, we have defined the distance between two vectors uv in an inner product space V. Three, we have defined what it means for a vector to be a unit vector. It means its length is 1 or its norm is 1. Okay, next is a remark. This remark says that actually we can change any vector v into a unit vector. If we find that it is not a unit vector, then we can change it into a unit vector. And how do we do it? This is a unit vector. To get a unit vector, we get a vector divided by its norm. We get a unit vector and then we divide it by its norm. Okay, so when we get the length of a unit vector, now here we are checking that when we do this, then we are getting a unit vector. Why? Because we know what shows that this is a unit vector. What shows that this is a unit vector is that we should be able to get its norm or length as 1. So let's compute the length of this unit vector of ours. It is the same as length here, and if it is raining in the whole village, then it is raining on each individual house. So we are here, and when we divide here, we get 1. So it means V is called a unit vector associated to V. So for any vector, whether unit or not, if it is unit, well and good. If it is not unit, we can make it a unit vector by dividing by its magnitude or its length or its norm. The process of obtaining a unit vector for a non-zero vector is known as normalization. So yeah, we want to make it a normal vector, a unit vector. So that process is normalization because we are using the norm. We divide by the norm, so that's why we call it normalization. Okay, example, we have an example. We have the vector space P2, the space of all polynomials of degree less or equal to 2. We are defining the inner product that when we pick two polynomials to return a scalar R, we get, we multiply their coefficients. Pick two polynomials, multiply their coefficients. These are constant terms. These are the coefficients of xc. These are coefficients of x squared. Where P naught is this and PQ is that. So we are letting our two polynomials to be this and that. We want to compute the inner product of PQ. We want to compute the norm or length of P. We want to compute the norm or length of Q. So you see, this definition is telling us that we multiply the constant terms together, we multiply the coefficients of x together, we multiply coefficients of x squared together. That's the definition. So here we go. The norm, the inner product of PQ is by definition given by that. And when we come back to our constant terms, we have negative 2 times 4 plus 1 times 0, because in polynomial Q, we don't have the coefficient of x there is 0. So plus 3 times negative 7. And when we do that, here we get negative 8 plus so we get negative 29. Next, we want to find the norm of P. The norm of P. Now we know. Yes, please.
Pardon, on the previous example.
Part A.
Yes.
Okay, part A, we want to find the inner product of P and Q. And from the definition of this inner product, we multiply the coefficients, like the coefficients of the constant terms together, coefficients of x together, coefficients of x squared, because the degree is less or equal to 2. So when you look at this polynomial and this definition, it means the inner product of P and Q is -2 times 4 plus 1 times 0, because the coefficient of x here is 0. In other words, we don't have x in Q. Then plus 3 times -7, and that one is giving us this as the value of the inner product of P and Q. Is that okay?
Yes, sir.
Okay, part B, the length. Again, from the definition of length, from this definition, we said length is the square root of u. The length of vector u is the square root of the inner product of u. So when I take this square root this side, it means the norm squared is inner product of u. So that's what we are using here, that it is inner product of P and P, but P and P means I multiply the coefficients. The coefficients P and P, it means it will be A naught, which is A naught squared, A1 squared, and that. So this is the 2 squared, which is -2 squared, which is 4, 1 squared, which is 1, 3 squared, which is 9. So when I add, I get 4. But if I want the length of P, then I need to take square root both sides. So the length or the norm of P is 14. Likewise, the norm of Q can be gotten similarly, and it will be 65. Now we want to ask ourselves, what would happen if we defined, so our norm had been defined by taking the sum, taking the sum of the product of the coefficients. What if we defined our inner product as the integral from -1 up to 1 of the product dx? What would be the values of what would be the answer in part A and part B? So you do that as an exercise. You'll find the inner product of PQ and the norm of P and the norm of Q using this definition of the inner product, not the one that we used. Okay, we have 3 minutes to our first break, whereby we have to reschedule to log, where we have to get a new login and come back. Hope you are aware of that. So properties of inner product spaces. If we let U, V, and W be vectors in a real inner product space, and lambda be any scalar, then the first property is that the inner product of 0 and any vector V, it is the same as the inner product of any vector V and 0, and it returns a 0. The second property is that the inner product of U, then V plus W, it can be distributed. So we get, if we have inner U, V plus W, then it is the same as the inner product of U, V plus the inner product of U, W. Third property, inner product of U times a vector that is equal to a vector times the inner product. This is related to I3. In I3, we had the constant at U, and this was the same result. But this property again is telling us that even if the constant is at the second vector, we really get the same result. This is the additivity property, but now we have the minus and we are starting with the first vector. So whatever works for addition also works for subtraction. So we get property 4, and this is also the version of Roman 4, so we surely get that. So those are the properties of all inner product spaces. So the proof of these properties can be done as an exercise. We have an inequality that we are calling the Cauchy-Schwarz inequality. It is also another property that if we have two vectors u, v, vectors in the inner product space, then the magnitude of this inner product space is less or equal to the norm of u times the norm of v. And the proof, I think our time is fast spent. I have 1 minute. So let's take a break and then we start from the Cauchy-Schwarz inequality. 3 minutes break. 3 minutes break and then we start from the Cauchy-Schwarz inequality.